Hello everyone. So in this video we are going to start with the continuous time Fourier transform. So in this video we will discuss about the continuous time Fourier transform. So in the previous video when we were discussing about the Fourier series, we saw representation of periodic signals as linear combination of complex exponential. So we deduce that any periodic signal can be represented as linear combination of complex exponential, and we derived the formula as well, and we will see in this video also those terms. And so how to represent an aperiodic signal? The question arises here that we have a representation of periodic signal in terms of combinations of complex exponential, then how we can represent the aperiodic signal? So in this lecture we will try to address this issue, that how to represent an aperiodic signal. So Fourier reasoned that an aperiodic signal can be viewed as a periodic signal with an infinite period. So we can have an alternative representation of aperiodic signal which can be viewed as periodic signal with an infinite period. So if we increase the period of a periodic signal and make it infinite, then we can say that it will represent an aperiodic signal. So as the period increases, the fundamental frequency decreases and the harmonically related components become closer in frequency. So we will see this statement we will see with the example as well. So and as the period increases and become infinite, the frequency component forms a continuum and Fourier series sums become an integral. So let's see this statement, like how an aperiodic signal can be represented in terms of a periodic signal. So for that example, we can recall our earlier example of a periodic square wave. So we will write the equation for that wave. It is equal to xt. It will take a value of 1 when t is varying from minus t1 to t1, and it will take a value of 0 when mod t1 is varying from t1 to t1 to t by 2. So we already derived the Fourier series for this kind of periodic square wave, but just to recall, we will just do a quick derivation for the Fourier coefficient of this kind of square wave. So the representation of signal can be viewed as it will vary from minus t1 to t1 and it will take a value of 1, and for all other values it will take a value of 0, and though it is periodic, so it will repeat itself after a period of t. So we will again get this square wave at a period of t, and it will happen so on for 2t as well. So for 2t again we will get a square wave. Similarly for the negative part, we will get a square wave again at minus t1 and at minus t2 and so on. So this will move like that. This is periodic for a period of capital T. So we have the formula to get the coefficient of any kind of periodic signal. So we can write that formula. We have an, which is equals to 1 upon t integration over period t xt e raised to the power minus jk omega naught t dt. Now we will first get the coefficient, which is a naught. So a naught can be represented what? It will be 1 by t. We will put the value of k as 0. So we will get integration, and it will be minus t1 to t1 because it is having a value of 1 only for the interval of minus t1 to t1. So from minus t1 to t1 we will integrate dt, and what we will get? We will get 2 t1 by t, and this is called an average value, which we have already discussed. And quickly we can get the expression for the coefficients when k is not equals to 0, and that will be equal to ak 1 over t summation minus t1 to t1 e raised to the power minus jk omega naught t dt. And when we solve this, we will get an expression which is, after rearranging, will be equivalent to 2 by k omega naught t, and then e raised to the power jk omega naught t1 minus e raised to the power minus jk omega naught t1 divided by 2j. So, and we have seen that the final expression for the ak will be equal to 2 sin k omega naught t1 by k omega naught t, and here omega naught is again 2 pi by capital T. So, this is just a quick derivation for the coefficients. We have already plotted the coefficient in our previous video. For brevity, I am not repeating the same. We will have a different interpretation for the same expression. So, earlier we have seen that it as a coefficients lying at different values. So, they are discrete values, but here we will have an alternate way of interpreting these samples. So, we will alternative way of interpreting is as samples of an envelope function. So, we will pick an envelope function. So, our envelope function will be of the form sin 2 sin omega t1 by omega, and we will take sample at every k omega naught, and that will be represented by t a k. So, this is an alternate way to represent this expression. This expression shows that every coefficient is discrete. For every value of k, we will get a coefficient, and here what we are saying that we will take an continuous signal, that is 2 sin omega t1 by omega, and we will take the sample of that envelope at every value of k, that is omega is equals to k omega naught, and that is the alternate way to represent it. So, how the what is here, that this is envelope of t a k. So, this expression is envelope of t a k, and a k is your samples of these functions. Okay. So, now let us plot in an alternative way. So, what we have told that we take the function, that is 2 sin omega t1 by omega. So, the plot will look like this. You can use any software to plot these functions as well. Just for a representation, I am writing, that is not an exact plot, but just a plot for understanding. Now, we will plot the coefficients as a sample of this function. So, this is a sample, this is again a sample, and this value is 2 omega naught. This is again minus 2 omega naught. So, these are the samples. For exact value, you can refer my previous video. Here just I am showing that we have represented the coefficients as your sample of this envelope function. And suppose we increase the period. So, now period is increased to a value. So, how the plot will look like? So, the plot for the increased value of t will look like. So, now we made it t1 as 4t. So, how it will look like? The graph, the envelope will be same, it will not change. So, the envelope will be same, and now the sample will increase and they come closer. So, here we will get different samples, and this value is now your 4 omega naught. This is your minus 4 omega naught. Similarly, you will get different samples here, different samples here, and so on. So, as you can see, as the period is increasing, so here t is increasing. So, you will get a coefficients which are closely spaced. So, as the period t increases, the envelope is sampled with closer and closer spacing. So, what this graph finally summarizes that as the period t increases, the envelope is sampled with closer and closer spacing. And this is shown with this graph as well. You can directly infer that now the envelope is sampled with different values which are very close. And if we make the value of t very large, so it will be very large, or we can say it will tend to infinity. What will happen? The signal will become an aperiodic signal. So, it will be only a rectangular pulse, and now as the period is now infinite, so it will analytically it will repeat itself after a period of infinite, but that is irrelevant. So, we will say that it is a rectangular pulse. So, aperiodic signal corresponding to a square pulse of a 1 period. So, this is basically representing aperiodic signal corresponding to square pulse, that is square periodic pulse of only 1 period. And as we increase t infinite, what will happen to the coefficient? Here we have seen that as we increase the t, the coefficients are become closer and closer, so that the envelope is now sampled with closer and closer spacing, and as we increase this infinite, the coefficient approach the envelope in some sense. So, suppose in this figure only, if we will increase the t at infinity, so it will be very closely sampled coefficients. So, and if they are so close that it will approach the envelope in some sense. So, if t raised to t tends to infinity, the coefficients approaches the envelope. So, now we will get the mathematical expression for the Fourier transform using this approach which we have discussed right now. So, what we want to do? We want to derive the representation for any kind of signal. So, suppose we want to derive a representation for this kind of signal. So, which is varying from minus t1 to t1 and xt, and this is your time axis, and this can be any arbitrary shape. So, it can be like this also, it can be even triangular also. So, any shape, it is just an representation of a signal which is having a range minus t1 to t1. So, and we construct a signal x dash t, which is the repeated version of this signal. So, with a period of t. So, we will get this kind of signal which will repeat this square pulse after a period of 2 and so on, it will move so on. And similarly for the negative part, so at minus t it will again give you a rectangular pulse, and it will repeat itself after every period, and it will move so on. So, this is the constructed signal x dash t, and it is equal to x t for a period. So, if we will just consider this signal for one period, so what we will get? We will get our x t. So, as we know that we can represent any periodic signal in terms of its Fourier series. So, x dash t can be written as summation k is equals to minus infinity to infinity a k e raised to the power j k omega naught t, and the coefficients can be represented as a k is equals to 1 by t minus t by 2 to t by 2 x dash t e raised to the power minus j k omega naught t dt. The period is t and we are taking minus t by 2 to t by 2. Just for the reference, you can take any of the interval. So, you can take a value of 0 to t as well to derive this. So, now since your x dash t is equals to x t for one period, and that is your period is basically minus t by 2 to t by 2, and it is 0 in all other interval. So, we can write a k as 1 by t minus t by 2 to t by 2 x t e raised to the power minus j k omega naught t dt. So, from this expression the x dash is now replaced with x t, because this is taken for a period of minus t by 2 to t by 2, and this can be represented as 1 by t minus infinity to infinity x t e raised to the power minus j k omega naught t dt, because we know that we have increased the t to a very large value, so that it became a aperiodic signal. So, the envelope of TAK, so envelope of TAK will be represented as some value x of j omega, and that is written as minus infinity to infinity x t e raised to the power minus j omega t dt, and the coefficients AK can be represented as 1 over t x of j k omega naught t. So, these are the two representations. So, suppose this is your equation 2 and we represent our Fourier series represented as equation 1. Now, we can replace this AK value in this expression. So, what we will get? We will get x dash t as summation k is equals to minus infinity to infinity 1 over t x of j k omega naught e raised to the power j k omega naught t, and here again omega naught is your 2 pi by t. So, we can replace that. So, our x dash t will be equal to 1 upon 2 pi summation minus infinity to infinity k is equals to x of j k omega naught e raised to the power j k omega naught t omega naught. And now, your x dash t will tend to x t as t tends to infinity. As you make the period infinite, your periodic signal can be represented as a aperiodic signal only for a period. So, and as t tends to infinity, your omega naught tends to 0. So, now basically what we have said that it will become an integral form. The summation is now changed to an integral form. So, now your x t can be represented as 1 by 2 pi integral of minus infinity to infinity x of j omega e raised to the power j omega t to d omega. And we have already seen the form of our x of j omega, which is equal to minus infinity to infinity x t e raised to the power minus j omega t dt. So, these are very important formulas, two important formulas, and we see how we derived it from our Fourier series expression, and we have approximated a periodic signal as a periodic signal for a period of infinite, and subsequently we got these two representations. So, any signal x t can be represented in terms of these two pairs. So, they are called Fourier transform pair. So, this is your Fourier transform and this is your expression for the inverse Fourier transform. So, we will use these formulas throughout to get the Fourier transform of various kinds of signal. So, we will start with some of the basic signals. So, first example which we will take as x t is equal to e raised to the power minus a t u t, and a is greater than 0. So, this is an exponential function and we try to get its Fourier transform. So, from the formula we know that x of j omega is equals to minus infinity to infinity x of t e raised to the power minus j omega t dt. Now, we will replace our x t with the given function, that is minus infinity to infinity e raised to the power minus a t e raised to the power minus j omega t dt. That can be written as 1 over 1 by a plus j omega, and this is a property from the integration. So, it will be equal to minus of a plus j omega, and your limit will vary from 0 to infinity. This is because of ut function. So, ut function will start from 0 and go up to infinity, and it will take a value of 1, otherwise it will take a value of 0. So, this range that is varying from minus infinite to infinite will change to 0 to 1. So, what we will get? We will get the Fourier transform representation of this signal as 1 upon a plus j omega, and here again a is greater than 0. So, now we have a Fourier transform of this signal. So, we can have, and that is complex. So, we can have an representation of magnitude of this function. So, magnitude of x of j omega will be equal to 1 over a square root of a square plus omega square. And what will be the angle of this? So, angle of your x of j omega will be equal to minus tan inverse of omega by a. And we can also see the plot of these two. So, the plot of these two expression can be represented as this. This is not the exact graph, it is just for understanding purpose. So, the graph will look like this for the magnitude, and this will be your a minus a, and this will be your a. This value is your under root 2 by 2a, and this peak value will be 1 by a, and this is your plot of mod of x of j omega. This x is your omega axis, and the phase graph will be very easy. So, it will follow a graph like this. This is your omega, this dashed line represent a value of pi by 2, this value is minus pi by 2, and the graph will take a value from pi by 2 to minus pi by 2, it will approach a value, and at minus a, so omega equal to a and minus a, it will take a value of pi by 4 and minus pi by 4 respectively. So, in this manner you can plot the magnitude and phase plot of any kind of Fourier transform which we get for any signal. So, now we will move to another example in which we will take a different signal. So, in the second example we will take a signal which is x t is equals to e raised to the power minus a mod t, and again a is equals to a is greater than 0. So, first we will see how the plot of this function will look like. So, this function has a plot of this. So, this is your time axis, and the function will vary from this value to an approach to 0 as t will tend to infinity. And what will be this value? This value is for t equal to 0, and that will be equal to 1. So, this is your x of t, this is your time x. So, this is the graph of this function, and now we have to take the Fourier transform of this function. So, how the Fourier transform will be calculated? We will again apply the formula for x of j omega, that will be equal to minus infinity to infinity e raised to the power minus a mod t e raised to the power minus j omega t dt. And from the property of modulus, it will have two range. So, one will vary from minus infinity to 0, and in minus infinity to 0 the plot will following a graph of e raised to the power a t. So, it will be e raised to the power a t e raised to the power minus j omega naught omega t dt. And for the other range that is varying from 0 to infinity, it is following a graph of e raised to the power minus a t. So, we will take e raised to the power minus a t e raised to the power minus j omega t dt. So, and then we will solve again in the similar manner. So, we will get a expression of a minus j omega plus 1 by a plus j omega, and that will be equal to 2a by a square plus omega square. So, the Fourier transform of e raised to the power minus a t u t will be equal to 2a by a square plus omega square for a value of a greater than 0. This is very important formula and can be used throughout the course. Now we will describe the Fourier transform of a very elementary signal, and that is very important also. So, we will take xt of our impulse unit impulse function, that is delta t. So, when we take the Fourier transform of this delta function, what will be? It will be minus infinity to infinity del of t e raised to the power minus j omega t dt, and this value is equal to 1. Why is it so? Because delta t when multiplied to any function will sample the signal at t is equals to 0. So, we have to put t equal to 0 in this. So, we will just left with the integration of minus infinity to infinity del t ut, and we have already seen in our previous video that will be having a unit area. So, that is why this value will equal to 1. And what does this mean? That it Fourier transform of 1 represent that it is having an equal contribution of all frequency component. So, equal contribution of all frequency. So, these are the example of some of the basic Fourier transforms.